one of the captains of this year's Northeastern Baja SAE team. Our 2020 vehicle
बाहर है शायद कार्तिक के साथ
Our 2020 vehicle is a two-wheel drive aft-braced vehicle with double A-arm front suspension and a 3-link trailing arm rear suspension setup. We began this season by analyzing our performance in the 2019 season. We identified acceleration and hill climb, pointed out above, as our two weakest dynamic events, both in California and Rochester. In both events, we finished lower than 30th place. With these weaknesses identified, we set about determining vehicle design requirements. Our primary goals were to achieve a sub-4-second acceleration time and gain a better understanding of the forces governing transmission behavior. In addition, we set a goal to decrease manufacturing time across all subsystems by 10%. As this does not directly impact vehicle performance, it was not included as a strict design requirement. Each subsystem generated requirements to achieve our overall goals, and despite the abbreviated season, we completed all research and design and are on track to meet our goals when resources are again available. Beginning with our overall requirements, based on our 2019 results, our primary overall goal was to improve acceleration performance. This drove the requirement highlighted above of not exceeding 325 pounds of total vehicle mass. The other requirements you see ensured that we would be able to pass tech and that we would be able to maintain performance throughout the entire endurance race. Research and development in each subsystem was designed to contribute to cutting weight and improving acceleration. The suspension and brake subsystems contributed primarily to cutting weight, while the chassis and drivetrain subsystems contributed to our acceleration improvements. Beginning with chassis and ergonomics, in 2018, we performed an investigation of the impact of drag force and weight on acceleration. Upon review, we found that it had been an overly simplistic investigation, and so in order to enable informed design decisions for 2020, we built an analytical model and performed acceleration tests at varying weights to quantify the relationships between drag force, weight, and acceleration time. This was intended to help determine if the added weight of gussets is worth the drag reduction achieved with a reduced firewall area. We started by designing a frame with a 7.7% smaller firewall area. This frame met Baja requirements to pass tech inspection and performed well structurally. Using our drag force model, we were able to quantify the impact of a reduced firewall area on the total drag force. We found that at 35 miles per hour, a smaller firewall yielded a 7% reduction in drag force compared to the 2019 vehicle. This works out to approximately 1/4 horsepower, which is significant considering we're working with a 10 horsepower engine. The results of the acceleration tests allowed us to define the equation characterizing the increase in acceleration time as weight is added. The graph and equation are shown on the right. Using the results from the drag force analysis and acceleration tests, we were able to determine that on average, a 7.7% reduction in firewall area is equivalent to cutting approximately 7 pounds from the total weight of the car. Given that the gussets added weigh a total weight of 2.18 pounds, that weight is offset by the benefits the drag reduction achieved with a reduced firewall area. Additionally, we removed 4 bracing members, eliminating 2 tubes, so the overall weight of the frame has not increased from 2019. By conducting a torsional test, we were able to confirm that removal of 4 bracing would not adversely affect torsional rigidity, and we were able to achieve improved acceleration performance without sacrificing handling and structural integrity. Moving on to suspension, the primary research project in suspension was shock characterization. For the past few years, the team has used Fox Float 3 Evol R shocks. To cut out the weight of the Evol chamber, we wanted to assess the possibility of switching to Fox Float 3s. Additionally, while we were happy with tunability and performance of air shocks, AFCO 63 series monotube shocks were even lighter and more cost-effective. In order to switch without a drop in performance, we wanted to identify spring constants that correspond to the current air shock tunes we run to aid in selecting springs that would achieve similar handling. After initial testing on the 2019 vehicle, we performed tests on an Instron machine, varying main chamber pressures and setting 2 different Evol chamber settings. We found that the difference in shock behavior with and without the Evol is minimal at the main 3 chamber pressures we run. The graphs are the raw data that we gained from those tests. We then calculated spring constants using the Angstrom data and found that those resulting spring constants are compared above. We used this data to guide what springs to purchase for initial AFCO testing. Ultimately, we were able to determine that the EVOL chamber has a minimal impact on performance and could be eliminated. And in addition, we identified 145 and 185 pounds-force per inch in the front and rear respectively as appropriate spring constants to begin coilover testing. Though brakes is a relatively light subsystem, cutting weight, especially in the front, is a benefit in that it reduces the amount of unsprung mass in the vehicle. We achieved this by switching to floating calipers and decreasing the thickness of our rotors. In addition to cutting weight, floating calipers allowed us to eliminate the hydraulic pass-through between the two caliper halves, the sealing of which we have had difficulty with in the past. We followed much the same process as we have in the past when designing custom calipers, using analytical models to determine hydraulic sizing and performing static stress and deflection analysis in SolidWorks. For the rotors, we performed thermal and buckling analysis, as our rotor material of 17.4 pH maintained mechanical properties up to 600 degrees Fahrenheit, so we needed to ensure that our rotors would not exceed 500 degrees Fahrenheit to maintain a factor of safety. Additionally, as thickness is reduced, the risk of buckling increases, and as such, buckling analysis was performed in SolidWorks. Based on the analysis results, the rotors were reduced in thickness to 0.085 inches. With regard to the calipers, the current simulation results are promising, and on-car testing will be performed when resources become available. Finally, in the drivetrain, the team felt that we had achieved as much as we could using intuitive guess-and-check tuning for our CVT. To guide design of tuning components for 2020, we determined that we needed to better understand the forces characterizing CVT shift. We hypothesized that a constant pinch force delta between the primary and secondary clutches would maximize shifting time and improve acceleration. We built an analytical model that used the engine output torque, assuming 100% efficiency, and the equations from the free body diagrams shown in the previous slide to calculate the sheave pinch force in the primary and secondary at various stages of shift. First, we used that model to characterize the ramp that produced the best performance in 2019. We then worked with the model to develop and test 3 more ramps, which are shown in images 2, 3, and 4. We fabricated the pinch force curves shown above, verified our hypothesis that a flatter curve would produce better acceleration. We then fabricated and tested each ramp on the 2019 vehicle. Our most recent testing with ramp number 4 allowed the team to achieve our best ever acceleration time of 3.82 seconds. In summary, by correlating test data to analytical model output, we verified our hypothesis regarding the relationship between the pinch force delta and acceleration time. With the research performed and the improvements made to each subsystem, we are projected to meet our goal of achieving a sub-4-second 100-foot acceleration time. We are also on track to meet vehicle target weight of 325 pounds, and we feel that we are well equipped with the knowledge necessary to achieve a successful tune for hill climb. Thank you for your time, and we'll take any questions now.
Thank you. I did have to mute quite a few people when we got started, so if you're stuck muted, just let me know in the chat, please.
How much weight did you lose or were projected to lose this year as compared to last year?
Last year's vehicle was 333 pounds, so we're projected to lose a total of 8 pounds.
Can you help us understand which systems were losing how much weight?
Yes, the frame is maintaining its weight from last year. We're cutting about a third of the weight from suspension, and the rest of the weight is coming from the drivetrain.
I would like to get a little bit more information on the aero modeling that you guys did and what kind of validation you did to confirm that it's valid.
I can hop back to that. So this is the model that we built for the drag. We treated the firewall as a flat plate with only a difference in area, creating the difference in drag force. So we calculated power loss and the quantifiable drag force with the two different firewall areas, the 2019 vehicle and the theoretical 2020 vehicle, and compared the difference in drag force and power loss. And then we performed an acceleration test. So we had one driver in the car performing 5 runs with different amounts of weight, so just gym weights added to the vehicle in 100-foot acceleration. And we measured all of those times, averaged them, put them on this graph, and got that equation for what the best fit curve was to relate the additional weight to acceleration time. And then using the 2 sets of data, we essentially calculated what the equivalent amount of weight loss would be to the benefits of having a smaller firewall. So we came to the conclusion that on average, having a smaller firewall gives us the equivalent in acceleration time of cutting 7 pounds of mass from the car.
I like the work that you've done here to come up with those numbers. Can you explain the trade-offs that you would have in overall chassis integrity and why you would choose that? And then in addition to that, any trade-offs you had with ergonomics by changing the shape of your firewall?
Yeah, so ergonomically, we didn't have any enormous difficulty because the only thing that we had to change was adding gussets to pass driver clearance. We determined that the weight of the gussets was the added gussets were only 2.18 pounds. So given that the benefits from decreasing the firewall area were much larger, we determined that it was acceptable to add the gussets despite adding weight. We also moved to a rear brace car. Previously, we were both fore and aft braced. We removed the fore bracing and eliminated 2 tubes. Let me hop to some backup slides real quick. We eliminated 2 tubes from a frame, which no longer are present in the 2020 vehicle. We did a torsional test to verify that removing those tubes would not impact our handling and our structural integrity negatively. This is an image of the physical torsional test setup. We have a fulcrum and the lever arm on the left, and on the right is the fixture, the clamping method that we use to constrain the rear of the vehicle. And then it's not very clear, but on either side of the ALC, we have 2 dial indicators to measure the deflection as we adjusted the amount of weight added to the front of the car.
Did you have to make any additional or different structural considerations to change from the air shock spring package to the AFCO spring shock package?
At present, no, because we're working with the same spring forces, the same shock forces that we were running before, because we intentionally chose springs that have the same spring constants as we had with the air shocks. As we do more testing, we might discover that the air shocks and those coilover shocks don't directly correlate that way, and we might find that we need to make some adjustments to the frame in future years, but we haven't gotten that far just yet.
You changed a lot with your suspension, you changed a lot with your frame. Can you talk about a time when the design goals for each system were in conflict with each other?
I think we had a little bit of conflict with the interest in decreasing acceleration time and the frame, because the decision to switch to a 4-brace car was a little bit difficult because it was a huge change and one that the team had never done before. And
That's all we have to time.
Okay.
Sorry, I meant to say a 30-second warning.
Thanks, Sal.
No
All right.
problem.
Good job, Emily.
Thank you very much.
Guys. Thank you. Very good job, Northeastern. You want to log off? We'll get the next team.